Hello everyone, I'm Qinghang Su. I'm from the Institute of Information Engineering, Chinese Academy of Sciences. It's my great honor to be here and share our work, efficient hashcode expansion by recycling old bits. First, I will introduce the background of hashing. Hashing can encode raw data into short binary codes, while preserving similarity relationship in the Hamming space. Due to its efficiency in storage and computation, hashing has been intensively studied and successfully applied in large-scale image retrieval systems. Recently, with the strong representation capability of the powerful convolutional neural networks, deep hashing methods can capture the underlying semantics of images. With the paradigm of simultaneously learning of features and hash functions, these methods can achieve satisfactory results. Figure 1 shows the basic framework of deep hashing methods with labels. For deep hashing methods, code length is a significant hyperparameter and has to be set before the training process. If retrieval accuracy is not satisfying, hash codes need to be expanded to achieve good retrieval accuracy. Therefore, code expansion is a common requirement in real application. However, as shown in Figure 2, when the hash code length needs to be expanded from k bits to k plus c bits, traditional methods have to retrain the models with new hash layers. The database images are required to be fed into the new models to generate hash codes with target code length again. For large image databases, the costs for regenerating the whole database codes are very high. To reduce the costs for updating database codes when code length increases, we introduce a novel deep hashing method for efficient hash code expansion, named Code Expansion-Oriented Deep Hashing (CEDH). CEDH can efficiently expand existing hash codes with no need to regenerate the whole database codes. An overview of the proposed framework is illustrated in Figure 3. CEDH mainly includes 4 parts. CNN learning part, which tries to learn a CNN model for query images. The hash layer of the CNN model is tailored to generate hash codes with target code length. Since there are no query images available for training, we sample the training set to generate query images. Projection matrix learning part, which tries to learn a code projection matrix for database images. Code expansion part can directly generate the new database codes by multiplying code projection matrix by the original database codes, and the expanded database codes can be formed by concatenating the original bits and the new bits. Finally, the learning criterion part aims to optimize the CNN model and the code projection matrix in an end-to-end way. We elaborately design a code expansion loss to learn the CNN model and the code projection matrix simultaneously. The code expansion loss consists of 2 terms, the similarity preserving loss and the quantization loss. The similarity preserving loss tries to preserve similarities between expanded database codes and query codes generated by CNN model. Since the original k bits of training codes are fixed, and the new c bits are generated through multiplication by projection matrix, the similarity preserving loss can be formulated as equation 2. The quantization loss tries to reduce quantization error between the continuous output of the CNN model and the binary hash codes. It can be formulated as equation 3. Combining equation 2 and 3, we can get the final formulation of code expansion loss as equation 4. the parameter gamma is utilized to balance the two terms. During the training process, we adopt an alternating strategy to optimize parameters theta of the CNN model and the projection matrix W. In theta step, we fix W and optimize theta with the standard backpropagation algorithm. In W step, we fix theta and reformulate the code expansion loss as equation 5. Then, calculating the partial derivative of the loss function with respect to W and letting it be 0, we can get the closed form solution of W as equation 7. After training, we can use the projection matrix and the CNN model to generate hash codes of database images and query images. For the database images, the new bits can be directly generated from the original ones by matrix multiplication. By concatenating the original bits and the new bits, we can get the final expanded database codes of the database images. For the unseen query images, we adopt the learned CNN model to generate their hash codes. Moreover, in multi-label image dataset, we find that trying to make the codes of similar images as similar as possible will cause similarity contradiction. As shown in figure 4, if we pull the code of A and B as close as possible, and that of A and C as close as possible, the code of B and C will be indirectly pulled together. However, the image B and C are dissimilar. To prevent the problem, CEDH maintains a certain distance between similar images according to their similar degree, and the similar degree is the cosine similarity between the one-hot label vectors of multi-label images. To evaluate the effectiveness of CEDH, we conduct extensive evaluations on 3 widely used image retrieval datasets: CIFAR10, NUS-WIDE, and ImageNet. Table 1 summarizes the MAP results with different bits on 3 datasets. From the results, we can observe that CEDH is able to expand original database codes to target codes while keeping the state-of-the-art retrieval accuracy. In Table 2, we list the MAP results of CEDH with different step size and step number on NUS-WIDE. In general, CEDH can achieve competitive performance with various step size and step number. To sum up, CEDH is compatible with a variety of deep hashing methods, and it can achieve competitive retrieval performance in almost all cases. Table 3 lists the code expansion time of CEDH and the corresponding backbone methods with GPU. As shown in the table, CEDH is 100,000 times faster than the corresponding backbone methods on GPU. We further report the code expansion time with different step size and step number in figure 5. In general, CEDH can achieve much higher code expanding efficiency than the corresponding backbone methods with both GPU and CPU. More specifically, CEDH is about 100,000 times and 1,000,000 times faster than the corresponding backbone methods with GPU and CPU. In figure 6, it can be observed that CEDH can coverage to a better MAP faster. This is mainly because CEDH can learn on the basis of the previous hash codes and doesn't need to retrain the model. In conclusion, both the training efficiency and the hash code expansion efficiency of CEDH are much higher than the corresponding backbone methods. In figure 7, we further investigate the sensitivity of the parameters lambda, gamma, and q on 3 datasets. All results are obtained by tuning one with the others fixed. From the results, we can observe that lambda and gamma have a wide range from 0.1 to 1000, and the MAP value increases with the increase of Q, meaning that sampling more query images can boost the query performance. Considering both computational complexity and retrieval performance, we set Q to 2000. In conclusion, CEDH is not sensitive to the hyperparameters, and it can achieve promising retrieval performance within a wide range. In Table 4, we list MAP results with different value of alpha in the proposed smooth similarity matrix on NUS-wide. Note that alpha is 1 is the conventional setting in previous deep hashing methods. As shown in the table, the cosine similarity-based solution can achieve the best performance in all cases with obvious advantages. We can infer that, on the one hand, the proposed smooth similarity matrix can tackle the similarity contradiction problem. On the other hand, polling hash codes of similar images to a certain degree determined by the similarity degree can benefit hashcode learning. Finally, we give some conclusions about CEDH. To our knowledge, CEDH is the first end-to-end deep hashing work for efficiently addressing hashcode expansion problem. A code expansion loss function is carefully designed to learn a code expansion matrix and optimize a CNN model simultaneously. With the learned code expansion matrix, code expansion can be efficiently achieved through simple matrix multiplication. Extensive experiments demonstrate that CEDH can significantly improve the efficiency of expanding hash codes with almost no loss of accuracy. Thank you so much for your interest and attention.